Hello and welcome to the last podcast for day 23, chapters 14 and 15. In this chapter, we're going to talk about something called nondisjunction and aneuploidy and how that results in monosomies and trisomies and polyploids. This is a pretty complex topic. So basically what I tell you in this podcast is what you're going to need to know. You're going to go much more in depth on this as you move forward with the curriculum. So let's go and get started. All right, let's begin this conversation with what is nondisjunction. Nondisjunction occurs during the M phase of meiosis. So let me draw real quickly here what's happening during metaphase. Remember in metaphase, this can happen during M1 or M2, but don't worry about that. Let's just look at it during metaphase 1. And remember, during metaphase 1, you have each homologous chromosome on either side of this center plate. And we have the centrosomes, remember, over here that send out the spindles and pull them over. And we know that there's a checkpoint here. We call it the spindle assembly checkpoint. And that makes sure that when this divides, each resulting cell gets one and only one of these chromosomes. What happens in nondisjunction is that either the spindle fails to attach to one of these, or they stick together. These two homologous pairs stick together. And so, if they stick together, let's draw what might happen. We have our center line here, and we may even have these two homologous chromosomes on either side. That may have worked out fine, but they're still somehow or another stuck together. So I'm just drawing a line. They're not connected, but during prophase 1, they kind of come real close to each other, and they can kind of stick to each other a little bit. All right, so now we have our spindles here, and it attaches here. And let's say that this checkpoint here fails because it doesn't attach to this one. It just fails somehow. What now happens is that this pole here is going to pull both homologous chromosomes to this side. And we're going to end up with something like this. Oops, that's drawn poorly. I'm going to draw that again. And we end up with something like this, where both chromosomes get pulled over to this side. And the other cell that forms, because it didn't pull any over here, it does not pull that chromosome over there. Right. This is called nondisjunction. They fail to undergo disjunction. This result is called an aneuploid. So just know that nondisjunction is a failure for the chromosomes to separate during meiosis. Nondisjunction means it's a failure to separate the chromosomes during nondisjunction. This leads to an aneuploid. And aneuploids, and in my examples here, I'm going to focus on humans, but recognize that nondisjunction occurs in all animals and plants. An aneuploid is anything that does not have the normal complement of chromosomes. So in humans, we would expect the progeny to have 46 chromosomes. Because of nondisjunction, you can see how we're getting fewer chromosomes in this case and more in this one. So you could have a case where you have one less chromosome, 45 chromosomes. This kind of aneuploidy is called a monosomy. Monosomies have one less chromosome. You could also see how this one might lead, if it's used during fertilization, would lead to an individual with one extra chromosome. And we call that trisomy. Now, what I drew up here is only one chromosome. And usually when nondisjunction occurs, it only happens with one chromosome. And that's why we come up with 45 and 47, because the rest of the chromosomes did exactly what they were supposed to do. It's just this one that caused problems. Now, in some very rare instances, we can have every single chromosome having a failure at M phase. at the spindle assembly checkpoint. And in fact, a lot of the plants that we eat are exactly this. And so in a human, if this were to happen, that individual would have one whole extra set of chromosomes. If they had a whole extra complement of both of them, you would have 92 chromosomes. And we call this individual a polyploid because they have more than just 2 copies of every chromosome, polyploid. So, nondisjunction, failure of the chromosomes to separate. This results in an aneuploid gamete, which will then, when fertilized, will result in a aneuploid individual. Individual humans, that is, they have 46 chromosomes. So we'll just say healthy. 45 chromosomes is if the individual is missing 1 chromosome, and they're called a monosomy. If they have an extra chromosome, they're called a trisomy. 92, a polyploid. Now, I should say, in humans, there's no such thing as a living polyploid. These all die at birth or before birth. A monosomy. In humans, we only see a monosomy with the X chromosome, and that's an XO individual, where they have 1 X chromosome and no other sex chromosome. And this syndrome is called Turner syndrome. Trisomy means that you have 3 copies of one of the chromosomes. Probably the best known example is having an extra copy of chromosome 21. So I'm going to write 21 here. So you have 3 copies of 21. 21 times 3. Chromosome 21 is in triplicate. And this is Down syndrome. Okay, now on the next slide, I'm going to talk about the very last point on your note-taking guide. Covers several points that we ask you to know, and I'm going to kind of go over those real quick with you here. The first was, how do they form? Well, these all form during nondisjunction, so let's not go over that again. But what are some risk factors? Well, probably the best known risk factor is related to maternal age. And over here, we're going to say percent Down syndrome. So I'm just going to put DS to abbreviate Down syndrome. And here we're going to put maternal age. And I'm going to put, around 30 here, age 30, 40, 50. The data looks something like this. It's not identical, but the percent of Down syndrome children at a lower age, maternal age, it's relatively low. And then they start going up at age 30, and then 40, and then by age 50, it's nearly 100%. Now, we do not see this as much with paternal age. And the reason we see it with maternal age is that, you have to remember that the oocyte begins its development. It begins its meiosis when it's as an embryo. So, for instance, the egg that created you, or the egg that created me, was first being developed when our mothers were a fetus in our grandmother. Okay, that kind of blows my mind every time I think about that. I'll say that again. The egg that went on to create me, for instance, first began its development in my mother when she was a fetus in my grandmother. Because of that, those eggs have been around a long time. In fact, what happens, we didn't go over this, but I should tell you real quick right now, is that meiosis in women, as they're producing eggs, starts as a fetus, and then it stops. And it doesn't start up again until an egg is released during the menstrual cycle. And so you may have 30, 40, 50 years that egg has just been in this arrested development. And something about being in that arrested development for such a long time really affects the viability of that egg. So the really most known risk factor is maternal age. The results of aneuploids, we already mentioned that on the last slide a little bit, but let me stress that again. In humans, surviving aneuploids is very rare. There's only, well, I think it's 4 common aneuploids that's trisomies that survive as that survived at birth, and that's when you have 3 copies of either chromosome 13, 18, or 21, or of the sex chromosomes. However, in these first 3 cases, 13, 18, 21, the phenotypes can be quite severe. In fact, most of these individuals don't even survive to birth. 13 and 18 are more severe than 21. And the sex chromosome, interesting, there's very little impact on those individuals. Okay, so in general, the trisomies, the result is typically quite bad for the individual. Typically, the way that they are detected, that's mentioned on your study guide, so I'm going to write that down here, detection, is that they can be detected by doing a chromosomal analysis using an amniocentesis. Sometimes they can detect some symptoms of it with an ultrasound, but it's not as conclusive. So there's different ways you can detect this before birth. The last thing on your note-taking guide that I want to just bring up real quick is this idea of what is the evolutionary advantage of this. When things persist, there's usually some kind of advantage. It's hard to imagine that there is any kind of advantage that as a woman gets older, that her eggs get older and she has an increased chance of having a child with some kind of chromosomal abnormality. There are a few ideas. We don't know for sure, but there are a few ideas. So go ahead and think about that. And if we have time, we'll talk about this in class. Okay, that ends this podcast. If you have any questions, please make sure you come see us. We'll be happy to help you. Thank you. Bye.